Hello, this is the screencast for the 6.1 notes. Unit 6 is on thermodynamics, and overall, this unit is going to have 7 to 9% of the AP exam weighting. There's 9 sections in this unit, and we're just going to cover section 1 today. Okay. So most of section 1 is just kind of some background information. There's really no calculations or anything. It's all conceptual. All right. So we're starting off with just some of the key terms that we talk about in thermodynamics. So 6.1, the title of this section is on endothermic and exothermic processes. So we start off with just the nature of energy, and just the term energy means the capacity to do work or to produce heat. The law of conservation of energy, that's something that we'll deal with a lot in this unit, is that energy can be converted from one form to another but can be neither created nor destroyed. And that goes for any chemical or physical process. If you're talking about nuclear, then it's a different story. But for chemistry, energy is going to be conserved. And then we have potential energy. Potential energy is energy due to position or composition. When you talk about chemistry, the potential energy is stored energy that's within the bonds of the molecules, okay? So chemical potential energy is energy that's stored within chemical bonds. So you'd probably want to jot that down. And then kinetic energy, so we've talked about that a little bit in terms of temperature and particle movement. But kinetic energy is the energy due to the motion of the object, and it depends on the mass and its velocity. So this equation, Ke, kinetic energy, equals 1/2 mv squared. That equation is in your equation sheet, on your green equation sheet. But kinetic energy for particles depends on the temperature of that substance, all right? So it's the average kinetic energy. So at a certain temperature, you're going to have an average kinetic energy. Some particles might be moving faster, some might be moving a little bit slower. But if you increase the temperature, the average kinetic energy is going to go up. Okay, and then temperature, that reflects the random motion of the particles in a particular substance. And again, if you increase the temperature, you're going to increase the random motion. And you want to understand that not all the particles are going to be moving at the same speed. Some will be moving faster, some will be moving slower. But at higher temperatures, on average, the particles will be moving faster. All right, and then heat. Heat is defined as the transfer of energy between two objects due to a temperature difference. And the heat is always being transferred from the warm object to the colder object. So we cover that later on, so that's not something you have to write down right now. And then thermodynamics, that term means the study of energy and its interconversions. So the next thing, state, function, and properties, that's the property of a system that depends only on its present state. Energy, which we're talking about a lot in this unit, is a state function. So there's a couple things you want to write down about state functions. One thing you want to jot down is that the pathway doesn't matter, all right? So the path doesn't matter. The only thing you worry about for a state function is the difference, where you started, where that property ended, and then the difference between those 2 points. It doesn't matter how it got there. It only matters the difference between the starting property and the ending value of that property. A lot of times with state functions, you see the delta sign. Delta means the change in something. So when you talk about state functions, you're talking about how that property is changing. So we represent delta, the capital delta, with a triangle in front of something. That means a change in something. When you see that Greek letter delta, that means you're dealing with a state function. So energy is a state function, enthalpy is a state function, we'll see that term later, and there's a few other ones that we'll see along the way, like later on, second semester, but energy is the first state function that we're going to talk about. And again, anytime you see that delta sign, the triangle, you're dealing with a state function, and with a state function, you're just worried about where you start, where you end, the pathway to get there doesn't matter. Okay, and then the next slide here, you got chemical energy. So when you're talking about thermodynamics, a lot of times you refer to the system and the surroundings. So the system is the part of the universe on which we wish to focus attention. So it's intentionally vague, so you can define the system as whatever it is you're looking at, all right? The surroundings is just considered everything else. The universe is the system and the surroundings. So when you're talking about energy being transferred, energy is either being transferred, if energy is flowing into the system, it's coming from the surroundings and vice versa, okay? So the system is whatever you're talking about. Usually for, when we talk about thermodynamics, we're talking about a particular reaction. So that reaction would be the system, and then everything surrounding that reaction would be the surroundings. Okay, and then the next thing we have exothermic. All right, now we saw this term a little bit in Unit 5, but exothermic means that energy is flowing out of the system, and it's going to be negative energy for the system. I'd like you to add to this that the energy of, when you're talking about exothermic reaction, the potential energy of the products is lower than the potential energy of the reactants. Okay, so please add that to exothermic. The potential energy of the products is lower than the potential energy of the reactants. So then that excess energy is then released to the surroundings. Going the opposite direction, an endothermic reaction, that's a reaction that absorbs energy from the surroundings, and that's considered positive energy for the system. So exothermic processes are negative energy, endothermic processes are positive energy. I want you to add to this too, is that the energy, the potential energy of the products is greater than the potential energy of the reactants. Okay, again, the potential energy of the products is greater than the potential energy of the reactants. So that energy is going to have to be absorbed from the surroundings. Okay, and that's energy going into the system, so we call that positive energy for the system. Okay, and then the energy gained by the surroundings must be equal to the energy lost by the system. That's that law of conservation of energy. Okay, and then in your notes we have this, you have a box that shows the system. We're going to add to that a little bit. But again, the system is whatever you're studying or looking at. The surroundings is everything else, and those two combined make the universe. And then thermodynamic quantities consist of two parts. So the magnitude, which we represent that with a number, and then the sign. And the big thing with thermodynamics and thermochemistry is just understanding which direction the energy is flowing. And the sign will tell you that. Just knowing, is the energy flowing into the system? Is the energy flowing out of the system? So you focus on the magnitude is given by the number, and the sign will tell you the direction of the flow, either into the system or out of the system. Okay? Okay, so that's all for that section of notes, but I want to go to, I want to exit out of here, and we'll go back to this diagram right here. All right, so I just wanted to focus in on this diagram right here that you have in your notes, and we're going to add a little bit to this, okay? So right now, this box is representing our system, okay? So that means everything outside of this box, that's going to be our surroundings. Okay, so everything outside that box is our surroundings. Okay, so now we talked about endothermic and exothermic. So you just want to be aware of what's happening in terms of the system for endothermic and exothermic. So when we talk about energy going in to the system, so energy is going into the system from the surroundings, that's an endothermic process. So let's write that down right here. Okay. And then when you're talking about energy flowing from the system to the surroundings, that's considered an exothermic process. Okay. So when you read these problems, for thermodynamics, you just got to be aware of the terminology, and that'll tell you is that energy going into the system, or is it energy going out? Is it endothermic or is it exothermic? When you talk about an endothermic process, that energy is going to be positive. Okay, it's going to be a positive value for the system. So an endothermic reaction means that it's positive energy for the system. Okay. When you're talking about the surroundings, it's always going to be the opposite. It would be negative for the surroundings. An exothermic process, that's going to be negative for the system. Okay. So endothermic reactions, those are positive values for the system. Exothermic processes, those are negative for the system. Some of the terminology that you might see in a problem that tells you it's endothermic, the most common one is probably absorbed. When it talks about heat energy being absorbed, that means that heat energy is positive for the system and is then endothermic. There's some other terms that are used too, so you just want to read the problems carefully and look at the terminology, and that'll tell you the direction of the energy flow. But probably the most common one is heat being absorbed by the system. If it talks about energy being released, that's usually referring to an exothermic process. So energy that's being released by the system means it's going to be negative for that system. And then another thing you see, if you were to do this in a lab, like if you were holding on to an endothermic reaction that's taking place in a beaker, it would feel cold. Okay, because it's absorbing energy from the surroundings, and when you're holding on to that reaction, you're part of the surrounding, so it's going to take heat energy from you and feel cold. An example of this would be like a cold pack, where you break that inner container, inner bag, and then it's a chemical reaction that is endothermic, and it absorbs heat energy from your injury, so it feels cold. Exothermic reactions, if you were holding on to that, say in a beaker or some other container, it would feel warm because that heat energy that's being released is going into you. Okay, so like hand warmers are probably the most common one that you're familiar with. So that's a chemical reaction that gives off heat. It's exothermic. It goes into you and makes you feel warm. Okay. Okay, so that's about it for the notes for section 6.1. All right, have a good day.